Okay, students, this is the second part of our Unit 4 lecture. And in this section, we're going to talk about the subject, which is stoichiometry. It's time for some definitions here, right? So, the amount of every substance that is used and made in a chemical reaction is related to the amounts of all the other substances in the reaction. This is because of the law of conservation of mass. Once you have a balanced chemical equation, you can use the coefficients in that equation to study the numerical relationship between chemical quantities in the chemical reaction. And this is what we call stoichiometry. Let's review something that we said in the previous section. How do you read a chemical equation? Remember, when we react, in this case, magnesium with oxygen to produce magnesium oxide. We can read the equation as 2 atoms of magnesium plus 1 molecule of oxygen makes 2 formula units of magnesium oxide. Or, like with any other algebra equation, you can multiply every term in the equation by the same factor and still obtain an equation. So we could say 2 times Avogadro's number of atoms of magnesium and 1 times Avogadro's number of molecules of oxygen makes 2 times Avogadro's formula units of magnesium oxide. But an Avogadro number of atoms or molecules or formula units is essentially a mole. So we could read the equation instead of in atoms and molecules. We could say 2 moles of magnesium plus 1 mole of oxygen makes 2 moles of magnesium oxide. And because we can convert between moles and grams, if we know the molar masses, we could also read this by multiplying times the molar mass of each one of these species as 48.6 grams of magnesium plus 32 grams of oxygen makes 80.6 grams of magnesium oxide. And all of these are perfectly correct ways of interpreting that chemical equation. One thing we cannot do is we cannot read the coefficients as units of mass directly. So to read the equation as 2 grams of magnesium plus 1 gram of oxygen makes 2 grams of MgO, that is incorrect. Now, when we do this stoichiometry or stoichiometric analysis, we're going to take advantage of the ratios in the chemical equation. For example, we can do direct mole-to-mole conversions. Let's consider this equation here, which is actually the combustion of octane, one of the main components of gasoline that fuels our cars. Remember, the ratio of the coefficients is going to act as a conversion factor between the amounts in moles of various reactants and products. In this case, for example, we can establish a stoichiometric ratio that says that for every 2 moles of C8H18, you produce 16 moles of CO2. So you can use that ratio, that equivalent statement, just like we did in unit number 1, and it can act as a conversion factor between the amount in moles of the reactant, C8H18, and the amount in moles of the product, CO2. So let's do a practice exercise. Suppose that we burn 22.0 moles of C8H18. How many moles of CO2 are formed? Again, let's look again at the balanced equation. And remember that there is a stoichiometric ratio of 2 moles of reactant. I'm going to go ahead and call it octane because it's easier to say, to 16 moles of carbon dioxide. We're going to set up our standard dimensional analysis process. We start with what they give us, 22.0 moles of octane. So in our conversion factor, we want to eliminate moles of octane and allow moles of CO2 to remain. So our conversion factor takes that ratio up there and puts the moles of octane in the bottom and the moles of CO2 in the top, so that when we multiply, the moles of octane will cancel out, and punch the numbers in the calculator and you get 176. In other words, the combustion of 22.0 moles of octane adds 176 moles of carbon dioxide to the atmosphere. Now, remember what we said before. Even though the mole is a very convenient unit for counting things, we don't really see moles. We cannot count moles either. What we typically measure in our activities is mass. So let's do stoichiometric analysis using masses. Methanol, which is used as a fuel in race cars, burns in air according to this equation, and you can see it there. If 209 grams of methanol are used up in the combustion, what mass of water is produced? So let's see what our roadmap is going to be. Starting with grams of methanol, I want to find out how many grams of water are produced. But remember, the chemical equation does transactions in the currency of moles. So you can't plug grams directly into the equation. It's kind of like, going to Europe on a trip and you had to convert your dollars into euros, right? It's a currency exchange. So in this case, we have to exchange the grams of methanol into moles of methanol so that we can then use the coefficients in the equation to find the moles of water, and then we have to reconvert that to grams of water. Let's look at the conversion factors. Of course, to convert from grams to moles, we use the molar mass first of the methanol. Then to convert from moles of methanol to moles of water product, we're going to use the coefficients in the chemical equation. And now to convert from moles of water to grams of water, we're going to use the molar mass of water. Notice that the flow chart and the identities of your conversion factors allows you to build your dimensional analysis roadmap. Okay, let's start with what they give us. 209 grams of methanol. Our first step is to convert that to moles. So we want to have grams in the bottom, moles in the top, and that's the molar mass of methanol. And as you can see, the grams of methanol will cancel out, and we are now in the currency of the chemical equation, which is moles. I need to look at the equation now, and it tells me that for every 2 moles of methanol that are burned, I get 4 moles of water. So let's put that conversion factor there in a arrangement that allows the moles of methanol to be canceled as units. Okay, we are at step number 3 here. The moles of water, just like the flow chart above indicates. Our next step is to use the molar mass of water to find how many grams is that. So in this case, we're going to put the molar mass on top and the 1 mole unit on the bottom so that the moles of water will cancel out as units. You want to make sure when you write these things, remember what I said in the beginning, always write out the full conversion factor with the units. It's very easy to lose track of things if you're just putting numbers. And it's also very easy to put your factors in the wrong order. In other words, to put what should be in the numerator, to put it in the denominator, or something like that. Our calculator says that this is 235 grams of water. That is already compensated for sig figs, and that would be the product that we get. Now, let's talk about real life. In a chemical reaction, the reactants are not usually going to be present in stoichiometric ratios. It is likely that one of the reactants is going to be completely used before the others. When that reactant is used up, the reaction stops and no more product is made. The reactant that limits the amount of product is going to be called the limiting reactant, sometimes the limiting reagent. During the reaction, the limiting reactant gets completely consumed. Any reactants that are not completely consumed are going to be called excess reactants. And once we know who the limiting reactant is, we can determine the amount of product that can be made from that amount of limiting reactant. And we're going to call that the theoretical yield. This is kind of like the maximum amount of product you're going to be able to get from the reaction given the amount of limiting reactant. Let's do a little practice exercise. So in one process, 124 grams of aluminum are reacted with 601 grams of iron 3 oxide. And there's the chemical reaction. By the way, this reaction is called the thermite reaction. I believe, if I'm not mistaken, that it's a reaction that's been known for a long time, and they used it in the in the days of the expansion to the west when they were building out the railroads, because this reaction produces a lot of heat. It is such an amount of heat that the iron product comes out liquid. And so they could use this reaction with pulverized aluminum and essentially these ores of iron 3 oxides, that they could use it to generate liquid iron with which they could solder the, kind of fuse the railroad tracks as they were laying them down. Anyway, enough history. What is the limiting reactant and what mass of aluminum oxide is formed? There are several ways of doing this, and there's also different kinds of questions you can ask with stoichiometry. But in the typical case, what we're interested in is how much product can we get. So what we're going to do is we're going to test out what would be the maximum amount of product that we would be able to get for each one of these two reactants. So for example, if aluminum is the limiting reactant, then it would predict a certain amount of aluminum oxide product if we follow the same roadmap that we tracked last time, that we drew last time, for going from grams to moles back to grams. Now, if it's the iron 3 oxide, then it would be the second roadmap here. The idea is that whoever was the limiting reactant will give you the lower amount of product, and therefore whoever gives you the lower amount of product, that tells you that was the limiting reactant. So let's start with aluminum here. Let's see what they gave us, 124 grams of aluminum. You see the roadmap there. Our first step is to convert that into the currency of moles so we can get on the toll road of the chemical equation. So aluminum is 26.8 grams. And then we're going to use the chemical equation to find the ratios. It tells us that it takes 2 moles of aluminum to get 1 mole of product. And then our product, aluminum oxide, has a molar mass of 101.96 grams per mole. Before we put numbers in the calculator, make sure that the units are properly canceling out. Okay, so grams of aluminum will cancel out. Moles of aluminum cancel out. And then moles of aluminum oxide cancel out. So at the end of the process, you have grams. Remember, in an exam situation where you're expected to display your calculations, it's very important that you show me your work, because that way, even if you have the wrong answer, at least I know that you were on the right path. Perhaps you put a digit in wrong. Maybe you mixed up, instead of 101.96, you put 101.69. Or maybe on the 124, you actually put 1244. Things that happen when you're punching numbers in a calculator, especially if you're feeling a little nervous or something like that. Okay, so the amount is 234. If aluminum is the limiting reactant, we would get a maximum of 234 grams of aluminum oxide. All right? Okay, let's try it out now with the other reactant, with the iron 3 oxide. Start with what they give us. Let's convert that into moles using the molar mass of iron 3 oxide. This time I'm going to track the units as I go, instead of doing it all together, all first and then canceling the units. My next step is going into the chemical equation. I see that there is a ratio of 1 mole of product for every mole of iron 3 oxide reactant. So that means the moles of reactant are going to cancel out. And at the end, I'm going to find out how many grams of aluminum oxide that is using the molar mass of this product. I notice that all of the units are properly canceling out. All that's left standing is grams of aluminum oxide. Result is 383. Who was the limiting reactant? Well, since the theoretical yield is lower for aluminum at 234 grams, then that means that aluminum is the limiting reactant. And that means that we are not going to get more than 234 grams of aluminum oxide product. We could ask another question. Since we therefore know that the other reactant, the iron 3 oxide, is in excess, how much is left over when the reaction stops? There are several ways you can do that, but one of them is to say, well, let's say that I got the 234 grams of aluminum oxide theoretically. I'm going to now go backwards in the chemical equation and ask, okay, so to generate this amount of product, how much of the iron 3 oxide had to react? So let's go ahead and convert this back into moles of aluminum oxide. Of course, the units cancel out there. And now let's use again the ratios in the equation. It's a 1-to-1 ratio. So, except that this time I'm moving from right to left in the chemical equation. So 1 mole of reactant was required for every mole of product. That means the moles of aluminum oxide cancel out. And now I'm going to find out how many grams by using the molar mass of iron 3 oxide. Moles of iron 3 oxide are going to cancel out. And punching the numbers in the calculator, adjusting for significant figures, I get that 367 grams of iron 3 oxide were used in the reaction with the aluminum that resulted in 234 grams of product being formed. Now remember, we started with 601 grams of iron 3 oxide. The question is how much is left over. So we started with 601, we used 367, and that leaves us with 234 grams of unreacted iron 3 oxide. Now, once more, let's go back to the real world. The theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant. Like we said, it is theoretical. But in real life, things can happen. You have incomplete reactions, or you have a side reaction that draws away some of the product, or things like that. One of the things you'll learn in lab activities, in your lab assignments, is that in the words of the Rolling Stones, you can't always get what you want. So the actual yield is the amount of product actually produced by the chemical reaction. And what chemists do is calculate the percent yield, which is calculated as follows. You divide the actual yield by the theoretical yield times 100%. That's just to adjust the decimal point. So let's say that in the previous example, we obtained 208 grams of aluminum oxide product. What was the percent yield? Remember, the formula is actual divided by theoretical times 100%. Our actual yield is 208 grams. Remember, our theoretical yield was 234 grams. Times 100%, 236 is about 88.9%. We have certain, parameters in chemistry, and sometimes in some reactions, based on experience, you might look at that and say, hey, that's pretty good. But it may be that in other situations, you turn this into your supervisor and they say, you know what, the other company, our competitors, they're getting like 93, 94% yields. You need to go back and see what is going on. So the percent yield sometimes tells you that you may need to tweak some aspects of your procedures. Okay, so now that we're done with that, we can proceed and look at reactions in solution.